Hello everyone, this is Mrs. Avon and welcome to Chapter 2, titled Representing Motion. What we will be studying in Chapter 2 is typically referred to as kinematics, and kinematics is just how an object moves. We are aware of all different kinds of motion. We see a car riding down the street. We've seen kids, or actually been on ourselves, a spinning ride at the amusement park. We've seen baseballs being hit for home runs. We've seen a child being pushed on a swing back and forth, back and forth. We will be able to study all different kinds of motion by the end of this course. But typically what we do in physics is we start with the least complicated situation of motion, and then we gradually add complexity to that simple model. We're going to be doing that with motion, and we're going to be starting with motion in a straight line. So in this section, what we're going to be doing is learning how to draw motion diagrams to describe motion, and then develop something called a particle model to represent a moving object. And then from there, what we're going to be able to do is answer some questions about the object in motion. Questions like where and when. So by looking at an object through a series of images, we call those images a motion diagram. It's going to show the position of an object at consecutive times. So we took 7 still images of this runner, we superimposed or overlaid them on top of each other, and then we look at the object's motion at different time intervals. And time intervals are typically represented with a delta t. A delta or triangle means the change in, something you certainly should remember from chemistry. And a time interval is going to be the final time minus the initial time. So if we were to mark this runner, we would have a t0, a t1, a t2, t3, t4, t5, and t6. So we have 6 different time intervals for this object. In the equation final minus initial, that can be t6 minus t5 if we're analyzing that interval, and so on. The big idea with a motion diagram or a particle model, which we'll talk about in a moment, is that the time interval between the objects, which would be the person, or the dots, are the same. So if this is a person running and there's 5 seconds between each dot, then t6 minus t5 would be t final minus t initial. That would give us 5 seconds. t3 minus t2 would also be t final minus t initial for that time interval and also give us 5 seconds. So the time between any two, t0, 1, 2, 3, 4, 5, or 6, will give us a time of 5 seconds. So we have to remember that when we're looking at these pictures, that the distance between them may change, but the time interval is always going to be the same. And these images are very useful in visualizing the actual object in motion. However, we don't typically draw the actual object every time we want to analyze a situation. We typically reduce the images to a single particle, and that particle is typically located at the center of mass of the object. For a person, the center of mass is about the belly button. For a geometric shape like a basketball or a baseball, it's typically the geometric center. So we really just want to look at the center of the object. And why, you might ask, would we do this? Let's take a look at a runner that's just running through the park.
My shoes, so you go ahead, I'll catch up. Okay. Come on, let's start running, let's go!
If we look at Phoebe running along the road or along the sidewalk, you can see that her arms are going in every direction, her legs are going in every direction. I noticed her ponytails flapping in every direction because she says she runs like a child. If we had to analyze Phoebe's entire motion, we would have to discuss those arms, those legs, her pigtails. So if we reduce every object to a dot, it simplifies the motion. The motion would be just a straight line. Okay. Another example, if you think of Ben Roethlisberger throwing a football, it's going to move in a nice tight spiral, we hope, and most of the time it is. We would have to analyze that spiral motion if we're looking at the whole football, Or if we take a look at somebody perhaps like me throwing a football, I didn't grow up with any brothers, so this is usually what you get. Yeah, it looks something pretty much like that. We would have to analyze the end over end motion of the football, and that complicates the situation. So we reduce everything to a single particle. And when we look at that particle model, we can discuss the object's motion. What we typically do, typically, oh, enough already, is we take the dots and we can analyze, because we know that the time between each consecutive dot is equal, and we know that the distance is represented by the space between the dots, is we can analyze motion. So if we look at number 1 here, the first few dots, what we see is that as you move in time this direction, the dots are getting closer and closer together. Okay. If something gets closer together, or if you travel less distance in the same amount of time, that means that the object is slowing down. So we can look from first red line to second red line and say that that object is slowing down. Then we have a series of dots between the next 2 red lines that are right on top of each other. That means that the object has stopped. Then the last 2 red lines, the dots are getting farther and farther apart. So all we're doing is looking at the relationship between the distance that the object covers and the amount of time it takes. And if you remember that the amount of time is always the same, that will help you answer some questions about the object. So again, object 1 starts out pretty constant, I guess because the dots are about the same distance apart. Then at some point they get closer together. So the object is slowing down, stopping, and then speeding up again for number 1. Number 2, those dots are equal distance from each other. So between the first 2 red lines, we have an object traveling at a constant speed. Then the dots get farther and farther apart, so the object is speeding up. In other words, covering more distance, always in the same amount of time. The third one, between the first 2 dots, I would say those are all equal distance. So it's traveling at constant speed. Then it slows down because the dots get closer and closer together. Then it stops. That's just a representation of many dots on top of each other. And then the last 2, it's going again at a constant speed. We can also talk about that constant speed. It has to be a slow speed because the dots are close together. That means it's not covering very much distance in the same amount of time. Whereas if we look up 1 at number 2, okay, these dots down here are all very close together, so that means it's traveling at a slow speed. These dots up here are farther apart, so it's going to be traveling faster. So just from a series of dots, using the particle model, we can tell a good deal about this object's motion. These are commonly referred to as dot diagrams. You'll also hear ticker tape diagrams or oil drop representations, because if a car were traveling and letting oil out at equal times. So they all give you the same impression of motion, but they are referred to with a couple of different names. So don't be confused if you see several different names for the same thing. Okay. When we look at these particle models or motion diagrams, we can actually also look at some quantitative data. So we can take actual data from a motion diagram by adding some numbers, and then we can begin to answer our questions more specifically. Where is an object and when is an object at that position?